Professor Bumbleweed here. A glass noodle that guides light sounds calm, yet it gleams the second someone bends it like a pretzel. That glow is not magic. It is physics with attitude, trapped light, tiny leaks, and lots of drama in glass. This topic stays a perfect mix of useful and petty. The cable mostly hides light, then a bend makes it shine and pretend it helps. You watch the core and cladding do total internal reflection, then watch leaks appear. Take a closer look now. Fiber optics works because of two glasses. Core inside, cladding outside. Their refractive indices differ slightly, and that small mismatch controls how rays bend at the boundary. Get the structure right, and the cable guides light across long distances with surprisingly low loss. If the beam hits the core to cladding boundary at the right angle, it reflects instead of leaving the glass. So the ray bounces down the fiber like a very disciplined pinball. That discipline explains how light stays guided over distance in telecom cables. As the angle changes, refraction turns into total internal reflection. Past the critical angle, light heading from higher refractive index glass toward lower refractive index material cannot transmit, so it reflects. Fiber optics uses that exact boundary behavior just stretched into a long, thin strand. This zigzagging is not a glitch. It is the whole plan. Total internal reflection keeps rays trapped in the core. Different launch angles create different paths, but they still stay confined as long as the boundary condition holds. Break the condition, and light leaks out. A perfect fiber keeps light inside, so it barely glows along its length. Real fibers have microscopic imperfections and bends, so a tiny fraction of light scatters out of its guided path. That leaked light hits the jacket and escapes to your eyes as shine. Fiber shines most when something upsets the optics. A tight bend forces rays to hit the boundary at worse angles, so more power leaks into cladding. A scratched or dirty connector end face also scatters light, wastes power, and makes random glow that looks dramatic and performs terribly. The light in a fiber carries data as pulses, not as one continuous beam. A transmitter makes the pulses using a laser or a light-emitting diode. The fiber guides those pulses by total internal reflection, and a photodetector reads them at the far end. Side glow is wasted signal. Even when light stays inside, different routes inside a wider core cause timing differences. That timing spread turns a clean pulse into a longer blur, which makes fast signals harder to distinguish. A narrower core reduces route variety, so pulses arrive more together and keep their sharp edges. Even with perfect guiding, light does not stay perfectly strong. Glass absorbs a little, and microscopic density fluctuations scatter a little, so power slowly drops with distance. That is attenuation. Side glow from bends is extra loss, stacked on top of normal attenuation, which is why careful routing matters. Practical rule: keep bends gentle and connectors clean. A dirty end face scatters light and makes the cable glow where it should not. Also, never stare into a fiber end. Telecom systems often use wavelengths that the eye barely sees, so no glow does not mean no light. Recap time. That frozen picture on the television shows core and cladding doing the heavy lifting. The refractive index difference enables total internal reflection, so light stays guided. When you see side glow, it comes from loss, bends, microbends, scattering or messy connectors. Shine equals leakage. If the explanation lands, hit like so the algorithm stops guessing and starts cooperating. Then leave a comment with a topic you want covered, because silent visuals need a mission. Otherwise, this turns into a mute professor doing interpretive science at a television forever. Until next time.